Cool. There we go. All right. Hi, everyone. My name is Irene. I'm currently part of the MIT Computational Psycholinguistics Lab, but I'll soon be starting my PhD in the psychology department at Yale. And today I'll be talking about teasing apart models of pragmatics using optimal experiment design. So when humans communicate, we convey and interpret meaning beyond what's explicitly said. So here's a really simple example. Say two people are looking at some trays. A speaker tries to refer to one of the trays by saying, "My tray has an apple." But there are two trays which have an apple, so the listener has to try to figure out which tray the speaker's actually talking about. There are many possible reasoning processes that the listener might undergo in order to draw a conclusion about what the speaker actually means. In the last 2 decades, there's been a concerted effort to create well-defined models of this sort of pragmatic behavior, particularly models which can make quantitative predictions about how humans compute pragmatic inferences. And because of this, there have been a number of proposals formalizing different theories of the reasoning process, and debates have also sprung up around which of these models might better predict human reasoning. So some popular models fall into these two main categories: the grammatical models and the iterated rationality models. So broadly, under the grammatical model, pragmatic implicatures are derived within the syntax semantics. A silent operator with a meaning similar to only is embedded in the sentence structure. So for example, the sentence, "My tray has an apple," might be interpreted as meaning "My tray has only an apple." The second category, iterated rationality models, or IRMs, propose that pragmatically enriched meaning is derived on top of semantic meaning. Speakers and listeners are modeled as cooperative agents that reason about each other recursively. So as you can see, these models outline very different theories about the reasoning process. Knowing this, the big question is, how should we compare different models as candidate theories of pragmatics? Typically, the issue of model comparison is approached in a couple of different ways. One way might be to handcraft an experiment to represent a particular phenomenon. For example, scalar implicature, or hyperbole, or free choice inference. You'll collect data, fit models to this data, and then evaluate how well these models fit to said data. Or another option is an experiment might be tailored to target a specific theoretical distinction represented by a model. And usually in these sorts of experiments, you're just comparing the model to some sort of baseline. But there are two main issues with this. First, different models often make similar quantitative predictions in a lot of cases, despite having very distinct theoretical frameworks. And second, it's often unclear how we can manually come up with experimental designs that are well suited to exposing qualitative differences between models. So even if we want to target a specific theoretical distinction, if that distinction is too subtle or too complex, it can be really difficult to come up with a good experiment that teases apart these differences. And because of this, we've ended up with large bodies of work that compare models conceptually and a sort of scattered and sparse landscape of empirical results. So we try to address these challenges by applying a framework for optimal experiment design to reference game experiments. We do this in order to systematically find reference game designs that will yield maximally different predictions between two models. This allows us to objectively compare models that are difficult to tease apart using typical methods. We'll apply this approach to several well-studied models, and we'll also gain new empirical insight into competing pragmatics theories. But first, a little bit of foundation. If we want to systematically find an optimal experiment design, we should first define the space of experiment designs that we want to work with. So for the purposes of this study, we chose to focus on simple one-shot reference games, which are a pretty popular tool for studying ad hoc scalar implicatures. We define a reference game with a set of utterances and a set of reference or meanings. The speaker attempts to communicate one of these meanings by selecting one of the utterances, and the listener observes this utterance and attempts to recover the speaker's intended meaning. The goal for both players is that the listener correctly recovers the speaker's meaning. As you can see here, the reference game can be represented pretty simply using just a binary matrix, which we'll call a lexicon. In our case, we focus specifically on the game from the listener's perspective. So in each trial, the participant will be prompted with a specific speaker utterance and is asked to choose the referent that the speaker is referring to. This experimental design consists of two parts: a binary lexicon and also a specific row of that lexicon corresponding to the utterance that we're going to use to prompt the listener. So let's return briefly to some existing models. As we mentioned before, we intend to demonstrate the OED approach by comparing models that can be evaluated using reference game experiments. Unlike grammatical frameworks, IRMs are specifically agent-based, and they also take into account the biased prior beliefs of the players. However, different IRM models also make different assumptions that lead to different reasoning processes. So the first IRM we consider is the iterated best response model, or IBR. Agents in IBR are primarily concerned with each other's actions. We'll start with a literal speaker based directly on the lexicon. Then at each iteration, the players choose the best response with respect to the actions of the other player in the previous iteration. Like all IRMs, IBR has this parameter T, which sort of represents how many rounds of iteration that the players are going to undergo in this reasoning process. Existing empirical data has commonly shown that humans actually undergo very few levels of reasoning. So for our purposes, we're just going to be stopping the models at T equals 1. Another popular IRM that you might have heard of is the Rational Speech Act model, or RSA. RSA players focus on each other's beliefs rather than actions, and they use Bayesian inference to define probability distributions over responses. Like IBR, we'll start off with a literal speaker, then a Bayesian pragmatic listener, and a pragmatic speaker. This pragmatic speaker is bounded rational with respect to a utility function, which we can see here. This utility represents the likelihood that the previous listener recovers the intended message upon observing the utterance U. And another important element of RSA is this free parameter alpha, which is a rationality parameter that represents the degree to which the speaker seeks to maximize this utility. Now, a recently proposed variant of RSA, RDRSA, grounds RSA in rate distortion theory, which is a subfield of information theory that's concerning efficient source coding between a target message, for example, a speaker's meaning, and a reconstructed message such as the listener's interpretation. With RDRSA, we try to derive optimal behavior from this independent information theoretic perspective. From this perspective, RDRSA seeks to minimize the following objective function, which jointly minimizes the number of bits required for communication and also maximizes expected utility. Here, the parameter alpha mediates this trade-off between communicative effort and utility. It plays a pretty similar functional role as alpha that we saw in RSA, but it has a somewhat distinct interpretation. And if we extrapolate from this objective function, we can actually derive the iterative process of RDRSA, which turns out to actually be mostly the same as RSA, except for its pragmatic speaker, which, unlike an RSA, takes into account the marginal probability of producing the utterance U. So now that we have a grasp on the models that we're considering, let's get into the process of finding an optimal design. So let's say we're comparing models A and B. For each design in the search space, we'll generate the predictions from both models, and we can then evaluate how different the predictions of model A and model B are from each other. And the optimal design is the one that results in the greatest divergence under this measure. We're going to focus on this bit of the process, specifically computing the divergence between two model predictions. The challenge here is how we should go about handling free parameters, which are parameters that can be adjusted after an experiment is run to fit the experimental data. One example of this sort of free parameter is the alpha parameter that we just saw in RSA and RDRSA. So let's suppose that one of the models, maybe model A, is the true model that perfectly predicts human behavior. We can set some parameters theta A and run model A on design D to generate the quote-unquote true results of an experiment with design D. So knowing this, is it possible to tell that a different model is an imposter model using this design D? Well, we can only tell that model B is not the true model if its best fit prediction is substantially far off from model A's quote-unquote true predicted distribution. There are many ways that we can quantify this divergence, but one really simple way is just to take the greatest difference in probabilities between elements of each model's distributions. But keep in mind that model A can vary based on its parameter values, so the minimized divergence also varies based on model A's parameters. So really, we want to find the expected value of the minimized divergence over model A's parameters. We can call this value the badness of fit of model B conditioned on model A. And for symmetry, we take into account this badness of fit in both directions and combine them to get a global utility function, which quantifies just how far apart model A and model B's predictions are for any given design D. If we maximize this global utility function, we'll end up with the optimal design that we want. In very simple terms, the optimal design is essentially just a design where both models are a pretty poor fit to each other's predictions. We're basically just minimizing the overlap in the predictions that these two models can possibly make for the optimal design. So now that we have this OED approach, we could actually use it to compare some models. We first compare across the grammatical and IRM model classes. So after running the OED approach to compare the grammatical model with each of the IRMs, IBR, RSA, and RDRSA, the same optimal design came out on top in all three cases, consisting of this lexicon and the highlighted row. With the lexicon and utterances, we can construct the following reference. And here you can see the distributions predicted by each model. As expected, the grammatical and IRM listeners make qualitatively different predictions for this design. When prompted with the utterance ball, the grammatical listener sees that, well, none of the reference contain only a ball, so it's not actually able to choose between R3 and R4, which both contain a ball, but also contain other features. We represent this indecision as a uniform distribution over R3 and R4. On the other hand, all three IRM listeners predict a preference for R3 over R4. Intuitively, the IRM listener infers that if a pragmatic speaker intended to refer to R4, they could have unambiguously used the utterance apple, which only occurs in R4, but they didn't, so the intended reference should probably be R3. After running the experiment, we can see that human participants chose R3 much more frequently than R4, which is consistent with the IRMs. So if you recall, RSA and RDRSA both make use of an alpha parameter. This plot here shows the correlation between the model predictions and behavioral data as a function of this alpha parameter. Starting with RSA and RDRSA, the best fit correlations for both RSA and RDRSA turn out to be very good, and they both achieve their best fit with human data at an alpha value somewhat higher than 1, which represents a trade-off that favors maximizing informativeness over minimizing communicative effort. This is consistent with existing empirical investigations of RSA-style models. The best fit correlations of RSA and RDRSA also exceed IBR and substantially exceed the grammatical model. These results suggest that probabilistic IRMs like RSA and RDRSA are better able to explain the human data than the non-probabilistic IBR or the grammatical model. So with those results, we kind of have an inkling that RSA-style models might outperform IBR, but we're also not entirely sure about how RSA and RDRSA compare. So we again applied the OED approach, this time to further tease apart those IRM models. Like before, we ran the OED approach pairwise on the three different models, and all three comparisons, coincidentally, produced the same optimal design, which you can see here. When prompted with the ball utterance, the IBR listener favors R4. Intuitively, the literal IBR speaker essentially chooses an utterance randomly out of the utterances consistent with its intended referent. So the speaker has a better chance of choosing an utterance like ball from a referent with fewer features. So in this case, R4 has only 2 features, while R3 has 3 features. So it seems more likely to the listener that the speaker is referring to R4. The RSA listener again abides by Garcian reasoning and favors R3, because if the speaker was referring to R4, they would probably have said apple and not ball. However, the RDRSA listener favors R4. If you recall, the RDRSA speaker also takes into account the marginal probability of each utterance. Because ball has a higher marginal probability to be spoken than apple, the pragmatic speaker gives the utterance ball more weight. So the RDRSA listener is a little bit more inclined to believe that the speaker might say ball to refer to R4. And after running the experiment, we see that human participants chose R4 more frequently than R3, which is qualitatively consistent with IBR and RDRSA, but not RSA. Again, we can look at the correlations over alpha, RSA, and here's RDRSA. So the best fit correlations for both RSA and RDRSA occur at alpha values extremely close to 0, which at first glance corresponds to almost entirely non-informative communication. However, compared to a literal baseline, RDRSA can achieve a better fit to the data for alphas ranging all the way up to 1, which turns out to be a fairly reasonable range. On the other hand, RSA is worse than a literal listener at any value of alpha. IBR is a little bit better than this literal baseline, but RDRSA still achieves a better fit for a fairly large range of alphas. And if we take a look at the RSA style models at a greater iterative depth, we can see that RDRSA has a better fit over a larger range of alphas, while RSA just gets even worse than it was at depth 1. These results lend empirical support to RDRSA over RSA and IBR. Finally, just to highlight a few major takeaways from this work. First, using the OED approach, we found empirical evidence that favors IRMs over the grammatical model, as well as evidence that favors RDRSA over RSA and IBR. This supports the proposal that rate distortion theory may help explain pragmatic reasoning. We also show that the OED approach can be used in practice for teasing apart models of pragmatic reasoning, which have otherwise been difficult to compare. And finally, our demonstration of this approach just scratches the surface of possibilities for application. It may be possible to leverage this approach not just to adjudicate existing models as we've done here, but also to aid researchers in theory building by identifying points of disagreement between model variants. The approach is also applicable at many different scales of comparison, from broad model classes all the way to within a single framework. In the future, we'd like to improve the scalability of the approach to multiple free parameters and larger lexica, which are conceptually pretty easy extensions, but are computationally very expensive. We would also like to apply the approach to more models and more reference styles. All in all, we hope that the OED approach can help facilitate more systematic empirical investigations of models of pragmatics. Thank you for your attention. Here's a link to the paper if you'd like to see it, and let me know if you have any questions.